Welcome to our review on nuclear equations. So as we've already looked at in a previous video, we've got these different types of radiation given off when unstable nuclei decay. What we're going to do in this video is have a look and see what happens in each of those processes in terms of the equations to show what happens to the materials involved. First one we're going to look at is alpha radiation. So in our alpha decay, we're emitting an alpha particle. And if you remember, the alpha particles themselves are made of 2 protons and 2 neutrons because they are a helium nucleus. So what I've given you in the next box down is the nuclear equation to demonstrate alpha decay. So we're starting off with one material and we've got its relative atomic mass and we've also got its atomic number there. Then it's going to make the alpha particle, which is the helium nucleus on the far right, and a new element. Because what we find is the mass numbers and atomic numbers on the left have to be the same as the total as the mass numbers and atomic numbers on the right. So we can see on the left we've got a mass number of 240. We know that helium has a mass of 4, so we can put that in, and that means that the mass number of our other element is going to be 240 minus 4, 236. Do the same thing with the atomic number. We're starting off with 94. We know that helium has an atomic number of 2. Therefore, 94 minus 2 gives us 92. And if we look that up on a periodic table, we'd find it's uranium. So when they give you one of these, they're likely to miss out 1 or 2 of the numbers on there, and you just need to work it out. So it's just adding or subtracting depending on which number they've made be missing. Our second type of decay is beta decay. So in beta decay, what we find is one of the neutrons in the nucleus is going to decay to form a proton and an electron. So if we start off with carbon 14, it's got a mass number of 14, then the end product will also have a mass number of 14. And the reason behind that is that even though we're losing a neutron, we are decaying that into a proton and an electron. And if we think back to what we know about our subatomic particles, both protons and neutrons have a mass of 1. So the mass doesn't change because we've lost a neutron, but we've gained a proton. So they balance out. Then what we need to do is consider the atomic number. So remember, the atomic number is our number of protons. If we're gaining a proton from the decay of our neutron, we need to add 1 onto that. And don't forget to write your beta particle, which is the symbol is a lowercase e, a 0 for its mass number, and minus 1 for the atomic number. The third type of decay we're looking at is gamma decay. So as a result of this, we're going to generate a gamma ray, and that's one of our electromagnetic waves. Now, because it's an electromagnetic wave, it has no mass and no charge. So we see no change to the mass or atomic number. So what we find is we have an unstable nucleus, and then the nucleus remains unchanged, same number of protons, same number of neutrons. The only thing we do is we lose a gamma ray. The final type of decay is neutron decay. So what we find is that the decay of some nuclei leads to the production of large numbers of neutrons. In order to make that atom stable, those neutrons have to be emitted. And a good example of this is helium-5. So we start off with our helium-5, mass number's 5, atomic number's 2, and then we're going to lose a neutron. So that's a mass number of 1, atomic number is 0. Take those off and we end up with 4 for our helium and 2 there. Hopefully at the end of this video you can describe in terms of particles what happens in alpha, beta and neutron decay. You can describe the changes in the mass and charge of a nucleus when the radiation is emitted, and write balanced equations for nuclear decay using the names and symbols of common nuclei and particles.